Test wrapper problem number 1. The problem states there is no general analytical solution for the motion of a gravitational system consisting of more than two bodies. However, there do exist analytical solutions for very special initial conditions. Here are 4 stars, each of mass m, which move in a plane of the page along the circle of radius r. Part A. Calculate how long the system takes to make one complete revolution. It's important to note that all the masses once again are equal to one another and that the velocity is constant for all the masses. To start, we take a look at one mass. Let's pick mass 4. We then draw all the forces acting on mass 4. There are a total of 3. A gravitational attractive force from M1, M2, and M3. Notice that the vertical components of mass 1 and mass 3 are equal and opposite. Therefore, they will cancel out. Also, since velocity is constant, we know that the parallel component of all forces is 0. This gives us our first clue that since there is only F net perpendicular, the sum of our forces will be equal to mv squared over r. We'll now sum our forces with the help of some trigonometry. Let's set up the triangles, and using Pythagorean theorem, we will find the lengths of all the distances between the masses. Starting with mass 1 and mass 3 first, we use Newton's law of gravitation to find the horizontal components affecting mass 4. Newton's law of gravitation is the g constant times mass 1 and mass 2, or whatever, times both masses, all over the radius squared. Since all the masses are equal, the multiplication of the both masses will be m squared. Now, in order to do this, we need to find the appropriate r in our gravitational formula. We know the magnitude will be r times the square root of 2, as we see in our drawing. To find the direction, we state that the cosine theta equals r over the square root of over r times the square root of 2. This reduces down to 1 over the square root of 2. We then plug this into our gravitational equation, and lastly multiply this result by 2, since this represents both mass 1 and mass 3's horizontal components. We get 2 times the gravitational constant, m squared, over r times the square root of 2 squared, times 1 over the square root of 2. Next, let's move to mass 2, which only has a horizontal component, the distance of the radius times 2. We plug this into Newton's gravitational equation and get g, the gravitational constant, times the mass squared, over 2r squared. We now have all our terms and set them equal to mv squared over r. We simplify, and we get our velocity. Now we're asked to find the period of one revolution. To do this, we use t equals 2 pi r over v. We plug in our velocity that we found, and we get the result that t equals 2 pi r over the square root of g times m over 4r times 1 plus 2 times the square root of 2. Part B. Part B states, unfortunately, this configuration of 4 bodies moving in a circle is very unstable. A short time later, one of these bodies is observed to move at constant speed along the path shown in the diagram below. On the diagram, draw a vector representing the net force on the object when it's at location A and at location B. Here is the answer. As stated before, we only have the perpendicular force to look at since parallel F net parallel equals 0. The perpendicular force always points to the center of the kissing circle. The size of the kissing circle tells us the magnitude of the forces. Since the radius of A is smaller than the radius of B, we know that the magnitude of A must be greater than the magnitude of B. As you see, all this is shown in the diagram, that the arrow length of A is greater than the arrow length of B. Thank you.